In the last video, we learnt how to interpret Bayes' rule as it applies to random variables, and we came up with a way of writing it that applies perfectly happily to continuous random variables, sidestepping any thorny questions about what it means to condition on events with probability 0. This is what we came up with. In this video, we're going to talk about how to actually use it in calculations. It may not seem there's anything much to it. It's a formula. It does what it says on the tin. You just bung in the expressions that you know and you read out the answer. But there are two niceties about working with Bayes' rule. The first is this denominator term here. It's a real pain, and you never want to work it out explicitly if you can possibly avoid it, because there's usually no closed form solution. Sometimes there are cunning math tricks, which we'll see in this video, and sometimes there are computational workarounds, which we'll look at in some later videos. The next thing is that it takes Zen level inner peace to really understand what it is we have on the left-hand side. This is a likelihood function for a random variable. If you just think of Bayes' rule as just a formula, then you'll often hit a dead end. But if you think of it as a way of finding the likelihood for a random variable, there are some cunning tricks we can use, as we'll see in the examples in this video. So let's get on with the worked examples. Consider a pair of random variables x and y generated by blah 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 blah. Calculate the conditional likelihood of x given y, or to say it in full, the likelihood for the random variable big X of value little x, conditional on big Y taking value little y. I skipped over all the text because every Bayesian question is actually exactly the same. You never need to bother reading it until you're actually working out the formulae. These are the steps for every single Bayes question. First step, write out the likelihood for x. Then write out the conditional likelihood for y conditional on big X equals little x. Then write out Bayes' rule. I've written it here in a slightly different form to what we had up a moment ago. I've written it here with a constant kappa, which incorporates that nasty denominator term, the likelihood of y. The point is, what we're trying to work out is a density function, the density of the conditional random variable x conditional on y. This is a function of little x. If you integrate it over little x, the answer must be 1. So we don't need to keep track of all the non-x terms, we can just derive them all from the requirement that the whole thing has to integrate to 1. So let's answer the question, let's fill in the pieces. We're told x is uniform from -1 to 1, so its density is a half. We're told y is normally distributed with mean x squared, so here's the conditional density of y, just the normal density function that you should know and love. Make sure you write it out properly. We're conditioning on the event that the random variable big X takes value little x, so the mean is little x squared. Don't put big X on the right-hand side here. There must be no random variables on the right-hand side. Next, apply Bayes' rule. As I said, we don't need to keep track of the non-x factors, so here I've gathered them all together, the kappa and the half and the 1 on root 2 pi sigma squared, and I've amalgamated them into a new constant kappa prime. There's no point writing out more algebra than I have to. Just one little nicety here. I want to stress that what we're interested in this expression is how it looks as a function of x, and we're treating y as a constant. Here I've just rewritten the exponent term to put x first. When we do maths, we're used to writing equations where the variable of interest comes first, so I just do it this way to make sure I'm thinking straight. So, finally, the constant kappa prime must be whatever it takes to make the conditional likelihood formula integrate to 1 when we integrate over x. In other words, it must be 1 over the integral of the expression we just derived. And we're stuck here. I'm sure Mathematica could solve this integral for us, but it wouldn't tell us anything useful, so we'll just leave it unsolved. What's actually much more useful than Mathematica is knowing how to approximate the integral using a computer, which is what we'll do in the next video. In an exam, it's generally okay to leave your base rule answers with a constant and just to write down an integral like this to show that you know in principle how to find the constant. Next example, though, is one where we can actually find the constant. Consider a pair of random variables theta, y. Find the conditional distribution of theta conditional on y equals 1. This question is worded slightly differently to the last one. Remember, the whole point of the previous video was that theta conditional on y is a random variable in its own right. It has a sample space and a likelihood function and so on. And the only way to make sense of Bayes' rule is to understand that it's a method for deriving the likelihood function of a random variable. And this wording here, find the distribution, is just a way to emphasize this idea, to get you to stop thinking of Bayes' rule as a formula for a conditional probability and start thinking of it as a formula for the likelihood of a random variable. So, the usual steps for any Bayes' rule question. First, write out the likelihood for theta. We're told theta is uniform in the range 0, 1, so the likelihood is just 1. Next, write out the likelihood for y, given that big theta takes value little theta. We're told y is binomial with parameter theta, so the probability of y equals 1 is theta, and the probability that y equals 0 is 1 minus theta. Next, write out the conditional likelihood of theta. The question actually asks us, find the distribution of theta given y equals 1, so here I'm just writing the y equals 1 case. We get the kappa times 1 times theta from the three terms, so simplify to kappa times theta, and we can get kappa as usual from the requirement that density for theta must integrate to 1. But there's another way to look at this answer. When you're doing anything at all in probabilistic machine learning, you always need to have a repertoire of standard random variables in your head. Whenever you see a density function, you should think to yourself, have I seen this density before? For pen and paper based questions, like you might see in an exam, there's one particular distribution that comes up again and again and which you should learn by heart. It's called the beta distribution. This is what Wikipedia tells us about the beta distribution. It takes two parameters, alpha and beta. For the beta of alpha, beta random variable, here's its probability density function. So let me rewrite the conditional likelihood function we just found in what looks like a horrendous overcomplication. I wrote it like this so that it matches precisely with the PDF that Wikipedia told us about. Our formula is kappa times theta, so let's call it theta to the power of alpha minus 1, where alpha is 2, and let's just invent a 1 minus theta to the power of 0 term, i.e. a constant, so that it matches up with the Wikipedia PDF. Remember, what we care about is how our likelihood function depends on the variable theta, and so what I'm doing here is I'm pattern matching our density with Wikipedia's density insofar as it depends on theta, or x as Wikipedia has it. Wikipedia also has this constant term 1 on b of alpha, beta at the front, so I'll include that too, and I'll compensate by multiplying by b of alpha, beta. So, why all this shenanigans? What I've done is I've coerced my likelihood function into the product of two factors, where the first factor is a constant and the second factor is exactly the density function for a standard random variable. We know that densities always integrate to 1. The right-hand factor integrates to 1 because it's a density already, so the constant on the left must just be 1. Because if it wasn't, then my conditional likelihood for theta would not integrate to 1. So, this is how we finish. We conclude that the conditional likelihood we were asked for is exactly the density of a beta of 2, 1 random variable. The question asked us find the distribution of theta conditional on y equals 1. That phrase, find the distribution, is a coded way of telling us, give your answer as the name of a standard distribution. Okay, now for a final example, we'll use Bayes' rule for classification. This is a data set of MP expense claims. I found that if I take the log of the claim amounts and plot a histogram, it looks like this. It's mostly a normal distribution, but there's an extra little hump around log of claim amount equals 2.8. So I decided to model log of the claim amount as a Gaussian mixture model. We came across Gaussian mixture models right at the beginning of the course in section 1.1. And when I fitted it, I came out with these fitted parameters here on the right. 96.6% of the claims belong to the big component, the k equals 1 component, and 3.4% of claims belong to the second component, k equals 2. I'm interested in what this second component might be, and so I'd like to be able to classify each expense claim according to whether it's k equals 1 or k equals 2. In Bayesian language, I want to know, given a claim amount x, in other words, given an observed value y equals log x, what's the probability that k equals 2? It's exactly the same 3 steps as for every single Bayes question. I don't want to go over it again because it's exactly the same as before, but this would be a good time for you to test your skill. Pause the video and see if you can apply Bayes' rule to get the probability we want. When you're ready, press play. There's nothing different here to what we've done before, except for the style of the equations. I've written them all out as case statements. One expression if k equals 1, a different expression if k equals 2. My random variable y is generated in 2 ways depending on k, so all my equations have 2 versions. So all of this is exactly the same as before. Now the last step, finding the constant kappa to make the conditional distribution of k sum to 1 when I sum over all possible values little k. And here's how we could find kappa in computer code. If I write out the 2 expressions as kappa times q1 and kappa times q2, then my code just computes q1 and q2. Then I set kappa to make kappa q1 plus kappa q2 equals 1. That's what we're doing on line 5. And then my final answer is just kappa times q2. The point here is that the random variable we're interested in, k, is a discrete random variable with a small sample space, in this case just 2 items. So we can work out the normalizing constant kappa by exhaustive enumeration, in this case by summing up q1 and q2. A common mistake I've seen students make is that they think to themselves, I only want to work out the probability of k equals 2 conditional on the data, so they only write out the first case, and then because they don't see the 2 cases, but they remember that something has to sum to 1, they do some bizarre tangled integral over x or y. The point is, you need to have a laser focus on what the variable is in the likelihood you're calculating. You're calculating the likelihood for k across all the possible values little k that it might take. The sum over all little k must be equal to 1. This is why I'm so keen on this likelihood notation, PR subscript big K, open brackets, little k. If you don't write it this way, then it's so easy to forget what the terms in the Bayes formula are doing and which of them are meant to sum up to 1. Okay, well, we've seen 3 examples. Let's summarize them. And in particular, let's review the ways that we can deal with this pesky normalizing constant. In the first example, we just had a messy formula for the conditional likelihood, and so we gave up. In the second example, we recognized our formula as being the PDF of a standard random variable, so we could straight away deduce the value of k. In the third example, there was only a small set of possible outcomes, so we could just run through them all by computer and choose kappa to make them sum to 1. Well, here there were only 2 outcomes, so we hardly needed a computer. This is totally different to the first example, where x was a continuous random variable, meaning it's just plain impossible to do an exhaustive sum. Now, in pen and paper exams, most Bayes questions will look like the second or third examples. But in real life, most Bayes problems are like the first example, and give up is not a satisfactory answer. What we need for problems like this is to find ways to work out kappa by computer even when the random variable is continuous. And that's the topic of the next 2 videos.